edge of my seat.
He gives us like,
But I don't know if you
Thank you very much, because that's the boneheaded mistake I made last time. I'm on a roll.
now it's rolling.
Yeah, all right.
Yeah, yeah. Yeah, no more labs now.
wait, is that, are we actually gonna have no more of that?
I think so, otherwise I'm not
It's not
helping.
possible, because we only have online classes tomorrow. Oh, I guess, yeah, it couldn't be on Monday. It would be due,
You know, there is an online version of every lab we've done,
That's
so
true. That's true.
that is always a possibility.
All right.
That would be suboptimal.
Could it always be a possibility?
indeed would be suboptimal. There are many things that are, I think, fall into that category.
Like this class being 8 weeks instead of 16.
Or every lab.
Don't forget, this class being 8 weeks is the school saying,
Yeah.
we
I know.
believe you can handle it.
I,
It's
They're wrong.
faith in
They're
you.
wrong.
Yeah, but do they know how many others we're taking?
Handling
Same
in
amount?
class is not major.
Clearly they haven't taken physics.
I think he did say that like
Classes
nobody who
training
made the
was science
decision
day.
had like was on the physics department.
I mean, maybe like English 111 or something, you know,
Oh,
would be a good.
I'm
yeah,
feeling in
cool.
calc too, but like this is like, oh.
Yeah, even calculus I was able to do really well easily. Whoa.
This is just a way. Well, I don't know how well you're gonna be able to see the white string, but
I'm sure there's good contrast there.
It's just like, are we gonna do,
Are you trying to get a level?
yeah.
You gotta come up just a
Oh,
tiny
up a
bit
little
more.
bit.
are we gonna make it vibrate
A
and
little
do like the?
tiny bit more. Right there. No, no.
Yeah.
Too far?
I think it looks good.
Looks good, yeah.
You use a foam level, you really wanna make sure.
It's physics, so you know perfection is gonna make the difference here. Yeah, one more.
Are we gonna make it like oscillate up and down?
We are.
And then
This
do-
is known as a string vibrator.
And then do like the, oh gosh, like this, is it gonna be a standing wave?
Well, let's find out.
I'm making a guess here, cause I watched a video about it yesterday.
Whoa.
Oh, that actually happened to hit a standing wave. I don't know, well, you can see it, it's a little bit off. We got a node here as opposed to there. We can adjust the tension just a little bit. Apparently not a whole lot in order to get that. But that's pretty close to, that's pretty much a standing wave. We've got a node here, 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 and here.
And it looks like it's a, what is that, a fourth harmonic, since there's like four little.
It is indeed a fourth harmonic, for a little bit of contrast there.
Can you just make the whiteboard black? Yeah.
Ooh, I can.
See,
Or at least darker. Add.
Isn't that black? Oh, there we go. I can see it better.
yeah.
Thank you.
Yeah, on the camera, I don't think it's really picking. It looks blue. But, all right, so we have a standing wave here. What's happening is the wave is being sent down. It's reflecting on the node at this end. This is a fixed end, and then coming back. If we adjust the tension, so we really don't have a standing node. We don't have it set up where it will be reflecting back at just the right moment. And if I keep adding tension here, because that last one was a fourth harmonic. I'm adding tension, I'm getting close to a third harmonic here.
Oh, so like it'll eventually, I'm guessing it'll eventually reach a second and then like a first.
Let's see, do I need to add a little bit more? Or? All right, that's a second harmonic there. So I have too much on here. These are designed to hook at the bottom also. Where's the then let's see if I can do it without breaking it. So far so good.
Almost there. Oh,
There you go.
All right, so we have a third harmonic. It's not as perfect as it could be. And in the lab version of this, you find, I think, 6 different harmonics, 5 or 6 different harmonics. And then you can do a graph and, you know, the little bit off here, a little bit off there, hopefully get washed out as opposed to adding to each other. But it is a little bit off. Well, let's just go ahead and just pretend for the moment that this is actually perfect. That's bugging me to pretend that's perfect, so that is worse.
What's wrong with it?
We're just slightly off on the tension. Looks like it was better like that. All right, so let's make a prediction. Let's see what the frequency is of this wave moving back and forth in order to be able to, well, I know what the frequency is. It's coming out of our sockets here, so it should be 60 hertz. Let's find out how close we get. And again, in the official one, you're doing a graph, and also we're not trusting that in the official lab, but we're going to trust it for right now because it's the process that's more important.
Wouldn't it be like 60 hertz, like, and then like some derivation off of that? 'Cause it doesn't run at like a constant 60 hertz. It runs at like, it dips and goes above, I guess. I learned that because I have a clock at home that runs off of the power line.
Oh, and you're saying it's just slightly off of 60 hertz?
Yeah.
Or that it fluctuates?
It,
Or both?
like it fluctuates, like,
Oh.
yeah. It's from like the 50s, so it has like a little motor in it that spins.
Might need an electrician out there or something.
It's supposed to be 60 hertz because ultimately the frequency depends upon, you've got basically a magnet, then you have something that's spinning the magnet, or, so either the magnet's still where you're rotating the magnet, one or the other.
Yeah.
But you've got basically wires that are rotating hopefully at 60 cycles a second.
I think I read somewhere though that like dips to like, I don't know, 59.998 or something. Like it's
That explains all the errors I've ever
it's
gotten from this.
it's very slight, but it never like stays a constant 60. I think I read that somewhere. I don't know. I could just be making it up.
All right, so what we have here is a wave that is being sent down to the other end and back. This is the one that we have right there was the third harmonic. Let's see if I can get a marker that actually will potentially show up. And as for the people who could see it, it physically looked like you had a situation like that. This was a little bit blurred as it vibrated back and forth. It obviously was not in two places at once, but it was going back and forth fast enough that the human eye just looks at it as sort of one blur here. As in reference to what we did at the end of yesterday, how many wavelengths is this?
Like
1.5.
1.5.
It's like 1.5 or is it 1.5?
It is.
All right, so we have, so the symbol for wavelength is that, and we got 1.5 wavelengths is the length from end to end. So let's measure what that length is. Actually, let's get the theoretical down and then we'll do the measurements. So my wavelength of this wave being sent down is going to be 2/3 of the length, which makes sense. I got 3 equal segments right here, and so 2/3 of it is a wave. Now I know that the speed of a wave, well, what is the speed of a wave? You got several different formulas from which to pick.
Wavelength times frequency.
Say it again.
Wavelength times frequency.
There we go. There's one of them, which derives from distance over time. And what's another formula for the speed of a wave? I have not talked about it to you directly. It has been, actually I think I got 3 videos deriving it. All right, just out of curiosity, how many of you have seen the video of the speed of a wave along the line, but just don't remember what it said versus, yeah. So how many feel like you've seen it, but just don't remember what it said? Okay, that explains.
Is that a wavelength over the period? Or is that not right?
So, in one period, so the time it takes to produce a wave, the wave has traveled a wavelength. So the distance is wavelength over the period, which is what you got written down. But 1 over the period is the frequency. So that's why this popped up
Okay.
there. Generally, when you're talking about the speed of any mechanical wave, and when I say mechanical as opposed to electromagnetic, so mechanical waves require a medium. They require some material that it's going to move through which it's going to move. Unlike electromagnetic waves, which is a 252 topic, that does not require anything to travel. It can go through space. Generically, I have 2 competing things when I have a wave traveling here. I have how much mass am I going to move? So the more mass there is, the slower it's going to be. And I also have, as one part of this moves, how much force does it exert on the next part? So if we're dealing with a transverse wave, which is what this is, as this piece of rope moves up, how much force does it pull on the next piece of rope, and how much force does that pull on the next piece? In other words, the tension. Or in this is where the lack of sleep kicks in. Or in the case of a longitudinal wave, as one part moves, how much does it push on the coil in front of it or pull on the coil behind it? So generically, there's some sort of force term related to the force of tension, in this case of the string, or in the case of a slinky or some other type of compression. I keep wanting to say compression wave. Longitudinal wave. Compression waves are a type of it. No, but how much force it's basically how closely are the particles next to each other, attached to each other? For instance, if I push on this table right here, the other end of the table moves pretty easily because the molecules are so tightly bound that when I push on one, it immediately exerts a force on the other. And the other piece of it is an inertial term. This is where the mass kicks in. So this is a generic for regardless of what type of wave you have. Now, specifically for this one, and there are, again, I believe 3 videos which go through the derivation of it, all different ways. In the case of a one-dimensional wave, it's the force, it's the tension divided by the linear density.
Is that a V or an X all the way over?
That's there?
Yeah,
That's a V.
okay.
I'm sorry, for Zoom, it's a little hard to see. What's the equation?
The equation I wrote is that V equals, so the speed of the wave equals the square root of a force term over an inertial term. And in the specific case of a one-dimensional medium, yes, I understand it's 3-dimensional. We'll talk about that in just a moment, I think. In the case of a one-dimensional medium, that would be the square root of the tension in the string divided by the linear density. And I use the letter mu for linear density. Certainly.
They're reusing mu.
Yep. Oh, just wait till 252. Mu is used for 6 different things.
Great.
Yeah, one of the videos I have for 252, I believe I titled it, "Don't Confuse These Mu's."
You also,
Don't use muse.
you also teach 252?
I have before. I don't know if I can't remember what my schedule is for the spring.
Use clues.
All right, so we have 2 different formulas here for the speed. We have a generic formula here for dealing with any type of wave. And then we have a specific formula for the one-dimensional medium. Now, I call it one-dimensional medium. There is a thickness to this string, and you could measure it. We know how. But if the thickness, or radius, however you want to look at it, is small, very much smaller than the length of it, assuming that it's a one-dimensional medium is legitimate. If you want to go through the 3-dimensional version of this, have fun. It's not overly complicated, but you'll end up with, wow, it would have been so much faster if we had just treated it like a one-dimensional medium. So what I'm going to do is I'm going to set these 2 formulas to equal to each other. So I have lambda f is equal to the square root of tension over linear density. Linear density, what is linear density? What is density?
Oh, Ford.
Mass over volume.
Mass over volume.
All right. So density, mass over volume. I don't know how well that can be seen.
Is that supposed to be a weird letter for density?
Oh, that's a rho. What did you use in chemistry?
D.
Oh. Barbarians. I rarely see D in physics. All right, so the density is mass divided by volume. That's just normal volumetric density. If we're dealing with surface density, put a sigma in there. Is there a way to make this? Oh, wait a second. I discovered this one.
Whoa,
Whoa.
that's advanced.
I don't know if that
Yeah.
seems like more contrast. I don't know if it helps them. So if that's regular density, what do you suppose surface density is?
Probably be the mass divided by the surface area.
Yeah, it's mass divided by the surface area. And linear density, what would you guess?
Mass divided by length.
Yep.
Except for what? What is the bottom one?
Linear density.
Okay.
So linear density is mass divided by length. And I found that in the experiment, this is the place where the biggest error occurs. Because the mass of a piece of string is so incredibly small. If you're just a little bit off, it has major implications. And being off could be because the balance is not perfectly balanced. And if you don't take that offset into account, you could be easily introducing a 30% error right off from the start. So my formula here is lambda times the frequency, wavelength times the frequency is equal to the square root of the tension over mass divided by length, or resolving that fraction, we have wavelength times the frequency is the square root of tension times length divided by mass. Since I am trying to find the frequency here based upon our experiment, I need to bring the wavelength over. So I end up with frequency is equal to the square root of the tension times the length over mass times the wavelength squared. And mass disappeared.
How did you put everything under the square root?
Taking the intermediate steps from this formula that we had over there, we'd have frequency is equal to 1 over the wavelength times the square root of tension times length over mass. And 1 over the wavelength is the square root of 1 over the wavelength squared. And so now I have radical times a radical, and I can just multiply the innards. That's how the lambda squared ended up in there. Or if I brought the lambda squared out, I'd have 1 over lambda on the outside, multiply both sides by lambda, and I end up back where I started.
Sorry, what the terms under the radical and the frequency equals 1/2?
That's a 1 over lambda.
Sorry, 1 over lambda, what are the terms of the radical?
Times the square root of, that's tension, times the length divided by mass.
Thank you.
So wavelength can't be negative?
No. I've never seen a negative wavelength. There might be somebody out there who's played around with that.
How did you get the L up to the top?
Because I got something divided by a fraction, so it was multiplied by the reciprocal.
Okay.
Or are you claiming that the math people have lied to me all these years?
I think you're just tapping into some really old math a lot of us haven't used since high school. Which for some of y'all might be like last year.
Yeah.
And for some of you, not
For
so
me, it's
recent.
not.